section 12.6 that we want to talk about today. Title is Chain Rules. The reason rules is, but we're going to find that there are an infinite number of chain rules for multivariable functions. Not like first year. In first year, you'd had a situation like y is a function of u, and u is a function of x, call that, say, z, and you said, if I want to calculate dz dx, chain rule says, you don't need the chain rule. Remember the idea of the chain rule first year was, if you wanted z as a function of x, this tells you it is. Y is a function of u is a function of x. So you can activate y of u of x and say, there. Every time you see a u in here, you put that instead, and now you would have z as a function of x and x only. But the idea was, if that's complicated, and that's complicated, you can imagine how complicated that thing is going to be when you take every complicated part of this and put that complicated thing. Chain rule says, you don't have to do that. If you want, you can get the answer by taking dz dy du, and then differentiating u with respect to x. Multiplying those two terms together gives you dz dx. So you're differentiating this complicated thing, you're differentiating that complicated thing, but you're not differentiating this really complicated thing. And that's what's a chain rule in first year. And the only thing that you could do is if you had an extra variable in here, then there'd be an extra term here, and that's all there was to it. For multivariable functions, possibilities are endless. So let's look at one to get us started. Suppose that I tell you that z is a function of u and v, and then I tell you that u is a function of x and y, and I tell you that v is a function of x and y. Right? This implies that z is a function of x and y. I could get it if I said every time you see a u in here, you put that. And every time you see a v in here, you put that. Oops, v is equal to h of x and y. So every time you see a v in there, you put an h of x and y. But you can imagine, if that's complicated, and that's complicated, and that's complicated, how complicated is that thing going to be? It's going to be really, really ugly. And I want you to calculate me, say, dz dx. Right? And you can do this, and you can go differentiate that respect to x, holding y constant, but it's going to be a real mess. So the idea is that we want a chain rule over here that's somewhat like this one here. And this is what it's going to be. And it is proved in the book, and I'm not going to prove it here in class. It says you differentiate z with respect to u, and then you differentiate u with respect to x. You differentiate z with respect to v, and you differentiate v with respect to x. And you add those things together, and that will give you the right answer. Now notice one thing in particular, that when you do this, chain rule, what would be in here? You differentiate that with respect, you'd have x's. This would have u's in it, right? If you did this and calculated dz dx, you would only have x's. But when you use a chain rule, you not only get the x's, you get the intermediate variable too. And look here, if you differentiate u with respect to x, then you're going to have x's and y's. If you differentiate v with respect to x, you're going to have x's and y's. You differentiate z with respect to u, you're going to have u's and v's. You differentiate z with respect to v, and you're going to have u's and v's. So you've got the ultimate variables here and here, and the intermediate variables here and here. Now there's a nice way to interpret these terms. I like to think of this is contributing to dz dx as those x's that get into z through the u, through here, right? X's are getting into z through the u and through the v. This one is accounting for those x's that get into the z through the u. This term is accounting for those x's that get into z through the v. Notice a nice thing back here. You could say if you put your hand over there, then that kind of agreed, dz dx and dz dx. You put your hand over here, that's a dz dx. You put your hand over here, and that's dz dx. So you kind of get an idea whether it's right or whether it's not. Proof takes a page and a half to prove this in the book, and I leave it to you. So there's one scenario. Right? Think about this, I said a minute ago, because I'm going to give you another scenario. And I'm going to tell you that u, or z, is a function of u and v. I'm going to tell you that u is a function of x and y. I'm going to tell you that v is a function of x and y. But then I'm going to tell you that x is a function of t, let's use p, and y is a function of t also. So a few more functions that we had in this example. And I want you to calculate, and notice I'm going to say dz dt. I'm not saying dz dt. If I were saying dz dt, I would be saying there's something to be held constant. But you can look at this and you can say, if for that you put this, right? Z is equal to f of u, which is g of x and y, and v, which is a function of x and y. So you could write that. But then every x and y could be replaced by this. See, the f of g of x and t, g of x of t, y of t, and h of x of t and y of t. And what would you now see? Now all you would be seeing would be t's. There's no other letter there, right? This is all t's, all t's, all t's, and all t's. So I can express z totally in terms of t, and therefore it's appropriate to ask for dz dt. There's nobody to be held constant. But again, if you did all of these substitutions, that could turn out to be just one horrible calculation to take the privilege. So we want a chain rule to do this. Well, I'm going to take the following approach. Same approach that I had there. I'm going to say, I must account in this derivative for all of the t's that get into the z through the u. So I'm going to have a term that looks like that, di z di u. And I'm going to write du dt. I'll talk about this again in a second. I want to talk about those t's that get in through the v. Then I'd have a di z di v dv dt. So that's reasoning like I had here. Take care of the t's that get in through the u. Take care of the t's that get in through the v. Now this I like. That one says, go differentiate z with respect to u. You gave it to me, I differentiate. This one, I like that one too. I just differentiate this with respect to v. What about this and this? This says go take du dt. But use a function of x and y. Oh, but use a function of x and y. And if I replace all these with t's, I would have x of t and y of t. And therefore it is appropriate to say du dt, differentiate this. But again, I don't want to do this substitution. So I'm going to replace the du dt by an appropriate chain rule. So I got a chain rule inside a chain rule. All right, so if we got this, we'll have to take care of in calculating du dt those t's that get into the u through the x. What do we have then? du, x, dx, dt. Would that look reasonable? And then similarly for this one. Oh, wait a minute, I didn't finish this one. I also have to count for the t's that get into the u through the y. So I'll have du, y, dy, dt. So that takes care of that one. Now we got a similar one here. Z, v. Now we're going to differentiate v with respect to t, thinking that v is equal to each of x and y, and x is a function of t, and y is a function of t. So we're calculating this derivative by using a chain rule. Well, we have v, x, dx, dt, v, y, dy, dt. There it is. There's the chain rule for that functional situation. And you can see it's starting to get complicated. The more things that you've got here, the more complicated this chain rule is becoming. Now, before I do some specific examples, I would like to show you that there is a very, very simple way to get the correct chain rule every time. It doesn't help you understand it. It just gets you the right answer. If you want to think about it and understand it, you go through the thought processes that we went through here. So let me show you this method. So the first example we had was that z was a function of u and v, and u was a function of x and y, and v was a function of x and y, and we wanted to calculate, say, di-z, di-x. And then we'll do a little bit of di-z, dy as well. You make what I call a schematic diagram. You put at the top the variable you want to differentiate, the z. You put underneath it the fact that it is a function of u and v. That's telling me z is a function of u and v. But u is a function of x and y, so I put that here. And v is a function of x and y, and I put that there. That's showing me that ultimately I could think of z as a function of x and y. And the requirement here is to find di-z, di-x. And here's the rules. You take every possible path through the schematic from the z, the guy you're wanting to differentiate, down to the guy you're differentiating with respect to, and therefore there are two of them. Those are the two paths from z down to x. And what you do is every time you encounter one of these line segments, you differentiate the top guy with respect to the bottom guy. So you write di-z, di-u. And then you have here, so now you've got another line segment, you write di-u, di-x. That takes care of this first path. Now you've got the second path, and so you add to that the second path, di-z, di-v for there, and di-v, di-x. That's it. And that's exactly the chain rule that I quoted to you a little while ago. So the schematic gets it to you very quickly. Doesn't tell you how you understand it, but we tried to reason what this term meant. And again, this is saying, this term is taking care of the z's, or the z's, the derivative of z with respect to x. The x is coming through the u. This term is taking care of the z, the x's that get into the z through the v. Right. Let's do that. At the top we have z as a function of u and v. We know that u is a function of x and y. We know that v is a function of x and y. And we know that x is a function of t. We know that y is a function of t. X is a function of t, and y is a function of t. So there's my schematic diagram. It's got an extra level compared to this one. And so we would say, you now want dz dt, and you can look at this diagram and it makes it clear. At the bottom, it is always t. dt's. So you can say I want dz dt. It is inappropriate to write dz dt. So I've got 4 paths. There's one, there's one, there's one, and there's one. And so if we take the leftmost path, we would have dz. And we're going to write di because you're different with respect to u, and therefore this guy's on the same level. He's been a constant, so this is a di. Then you're going to say this one, that's going to be di u di x. And again it's a di because there's a y to hold constant. And then you're going to have a dx dt. There's path 1. And if you look over here, that's that one. Now we got path 2. Path 2, that one. Di z, di u, di u, di y, dy, dt. And that is that one. And finally 2 more. Di z, di v, di v, di x, dx, dt. And finally the last one. Di z, di v, di v, di y, dy, dt. And that's exactly these other 2 terms that we have here. So again, this is a very nice, simple way to get the correct chain rule in a complicated functional situation like that. Again and again, and I repeat, does not help you understand, right, what these terms mean, but hopefully from what we said, you get an idea of what that means. Let's look at this one. I'm still not down to doing any specific examples. I want to get us used to setting these up, and then we can put in some actual functions. Suppose I tell you that I've got z. Z is a function of r and s and x. And I tell you that r is a function of x and y. And I tell you that s is a function of x and y. And I want us to calculate 2 things. Di z, di y, and di z, di x. I want us to calculate those 2 partial derivatives. Right? Schematic. Z on top, R, S, and X. R is a function of X and Y, and S is a function of X and Y. So if we want di Z, di Y, we will take all possible paths from Z down to Y in the schematic, and there are 2 of them. So we would have di Z, di R, di R, di X. That would be, oh, I'm doing Y. That would be that path there. Then we have added in black the other path, di Z, di S, di S, di Y for the second path. That one, straightforward. Now let's do di Z, di X. But now when you look, there are 3 paths from Z down to X's. So let's write those. Di Z, di R, di R, di X, di Z, di S, di S, di X, and then di Z, di X. How does that look? Now, somebody out there should say, we got a problem. This is the same as this. So cancel. No. I'm not sure what you got if you cancel it. The question is, why has that happened? And remember I had this notation earlier in the video, that if you want to differentiate with respect to x, the f with respect to x, and hold y constant, you could put that there to indicate that. That would be an excellent idea here. If I put here, right, that bracket, what is going there? What I'm saying here, differentiate z with respect to x, whom I am implying is to be held constant. Remember what the chain rule is doing. The chain rule is saying, it's saving you picking this up, and putting it here, picking that up, and putting it here. But if you did that, would you not see x's and y's? So this means differentiate z with respect to x holding y constant. Where did this come from? It came from here. It says you differentiate that z with respect to x, and you hold those two guys constant. So here, it's RS. So you can see this guy is not the same as that one, right? This one's saying hold y constant. This is saying take that thing there and differentiate with respect to those x's. You hold those guys constant. Because remember, this term is taking care of the x's coming through the r. This term is taking care of the x's coming through the s. And this term is taking care of the x's that are already there. Three ways the x's get into the z. These three terms take care of it. So this and this are not at all the same. So hence, it would be a good idea to do this here so that we wouldn't get mixed up. All right, let's take a couple of specific examples. We'll have to develop a chain rule, and then we'll do the calculations. Suppose I tell you that u is equal to rx times the square root of y squared plus z squared. I tell you that x is equal to s squared plus t squared. I tell you that y is equal to the sine of st. And I tell you that z is equal to the logarithm of 2t plus 2. And I asked you to calculate di u di s, and I asked you to calculate di u di t. So let's make up our schematic. U at the top, function of x, y, z. X, function of s and t. Y, function of s and t. Z, function of t. So there's our schematic for this particular functional situation. So if we want di u di s equal to all possible paths from u down to s, 1 through x, di u, di x, di x, di s, 1 through the y's, di u, di y, di s, and that's not one. So all we have to do is calculate these four derivatives, and we'll have the answer. And the chain rule again is designed so that you don't have to do any substitutions. You are simply going to now differentiate the functions as given to you. That's the purpose of the chain rule. So we want di u di x. Di u di x is the square root of y squared plus z squared. Differentiating that with respect to x. Multiplied by di x di s, 2s. Plus di u di y. Now we have to differentiate this thing with respect to y. Bypass the x. Bring down the power. Lower the power by 1. And then differentiate what's underneath the power, 2y. So how does that look for the derivative of this with respect to y? Now to be multiplied by di y di s, differentiating that with respect to s. That's a cosine of st, and different respect to s, atl in front. So there it is, unsimplified. Other one, di u di t is going to be all possible paths from u to t. There are 3 of them. Di u, di x, di t, di u, di y, di t, di u, di z, but this time dz dt. Right? So three possible paths. Calculating then. Di u di x, we already did that. That was this square root of y squared plus z. Times di x di t, 2t. Plus di u di y. We already did that one too. That was this one, right? That was di u di y. So cancel, cancel. xy over the square root of y squared plus z squared. Multiplied by di y di t. Cosine. st with an s in front. That's that. Plus di u di z x. Bring down the power. Lower the power by 1. Differentiate what's under the power. 2z. That's di u di z. Multiplied by dz dt. 2 over 2t plus 2 for the derivative of the log. And there it is, unsimplified. Getting the idea? One last one for this video. Suppose I tell you that u is equal to x squared y plus y e to the 2tx. I tell you that x is equal to b sine of 2t, b cosine of t, and I tell you that y is equal to the cos cubed of 14. Is it appropriate for me to ask for du dt? Is that appropriate? What you would be saying is that you can express z, or u rather, totally in terms of t. And that's reasonable. If every time I saw an x in here, there, I put in this. Every time I saw y, I put in this. I would have it totally in terms of t, and therefore it's appropriate to ask for d rather than dot. Schematic. U. It's got in it x's, got in it y's, got in it t's. X's and y's and t's. X is a function of t, and y is a function of t, and that's it. So schematic says all possible paths from u down to t, and there are 3. So I often like to do this, just to remind myself that I should have 3 terms in the chain rule when I'm done, because I might get involved in one and forget what the others. All right. So for the first path, di u di x dx dt. Second one, di u di y dy dt. And finally, di u di t. And again, notice the difference. This is saying u only in terms of t. This one is saying differentiate u with respect to t, holding the x and y constant. So you could put that there for emphasis. So all we now have to do is calculate all these derivatives to get the answer. Di u di x, 2x y t, plus, with respect to x, 2y t e to the 2tx. There's that. Di x di t. I have to differentiate, not di x di t, dx dt. Differentiating this, product rule. 2 cos 2t cos t minus sine 2t sine t. How does that work? The derivative of this with respect to t. So that took care of this one. Now this one, plus di u di y. Differentiate this with respect to y. x squared, with respect to y, plus e to the 2tx, multiplied by dy dt, differentiating that. Bring down the power. Lower the power by 1. Differentiate cosine 4t. Minus 4 sine 4t. How does that look for that one, for the derivative of this one? Brought down the power of 3. Lowered it to 2. Differentiate the cosine, turn to a sine, that looks good. Plus, finally, last one, di u di t. Differentiate this with respect to t, holding the x's and y's constant. You're gone, plus y, 2x e to the 2tx. Differentiate that with respect to t. Right? How's that? Now, I don't want to do this, but perhaps it might say here, let's do something, okay? Let me carry this example a little bit further. Say, let's calculate this when at t equals 0. Calculate the rate of change of that function u as a function of t when t is equal to 0. So we have no problem calculating this for t equals 0. Every time you see a t, you put in 0. But you also have terms that have x's and y's, so you'll have to take this value of t, get the x, get the y, all right, and use those as well. So we'll have to have x at 0. X at 0, plug in t equals 0. That's nice, that's gone. Y at 0, put in t equal to 0, you get the cosine of 0 cubed, which is 1. And therefore, u primed at 0. Perfect language to write that, what we like, du dt, evaluated at t equal to 0. So we'll simply take our answer there. Every time we see an x, we put in 0. Every time we see a t, we put in 0. And every time we see a y, we put in 1. All right. X equals 0, you're gone. T equals 0, you're gone. That's gone. All right. This one, x equals 0, right? And then we're putting x equal to 0 and t equal to 0. That's going to be 1. Oh, but wait a minute. If we put in t equal to 0 here, you're gone. So you're gone. Finally, this one, but x is 0. It's 0. That was fortunate. It's 0. Everywhere we substitute, we get a 0. I wanted a t equal to 1. Well, then we're not going to have zeros, right? All right, that's it for that video.